Okay, today's video is going to be about orbital motion, so it's a continuation of universal gravitation and more specifically gravitational field sections of Physics 30. There's going to be a little bit of videos stuff online on April 23rd, so I'd recommend you watch one or two of them. So this video history is actually really interesting. It's not overly graphic heavy, it's just a man talking for about 11 minutes, but lots of neat stories about what's going on and how our solar system came to be in the sense of how we understand our solar system. There's some textbook readings online, as well as some animations about Kepler's laws, and a version of these notes can also be found. Again, that's on April 23rd. So let's begin. The Copernican revolution. So I'm not going to get into details about this because, as I said, there's an 11-minute video that I will also put down in the description of this video. You should probably just watch. It's a much better rendition than what I would give you. But the really quick of it, once upon a time, people used to think Earth was the center of our universe, or our solar system, if you will. Then eventually a man came around by the name of Nicholas Copernicus. He said otherwise. He was viewing the stars and the moons and all the other planets that he could see with his, just his eye at that point. And he kind of came to his own conclusions and says, I don't think that Earth is the center. I think it's actually the sun. And he wasn't liked by many people because of that. I won't get into details. It wasn't until a little while later, as you can kind of see by this rough timeline, a man by the name of Galileo Galilei took his looking glass and pointed it to the stars, and therefore became the first telescope, and one of the first known people to actually start looking into the heavens, if you will. And he noticed there was mountains on the moon created by little meteors, and there he kind of backed up Copernicus' idea that Earth is not the center of the solar system. So watch that other video. He goes in a lot more detail than my little rendition. Sooner or later, a man by the name of Tycho Brahe, or Brahe, it depends on how you want to pronounce that. I've always been told it was Tycho Brahe, but the video I'm linking to says otherwise. He disagreed with Copernicus. He said that it's actually Earth is the center of the solar system, and his math, he had some decent math to back it up. But it wasn't until one of his pupils, Johannes Kepler, actually really put the nail in the coffin, so to speak, to kind of really solidify that no, Copernicus is right. The sun is the center of our solar system. And that's what the focus of today is. And then Newton, of course, took Kepler's work, Tycho Brahe's work, Galileo Copernicus, and came up with his laws of universal gravitation. So Newton was pretty famous for saying that he only did as well as he did because he stood on the shoulder of giants. So here's some of those giants. So moving on, this is what Johannes Kepler looks like. Strapping young lad, nice mustache. He has three laws of orbital motion, three laws of planetary motion, if you will. So law one and law two, and you don't have to worry, there's not going to be a math for that. Law one just says passive planets are ellipses with the center of the sun at one focus. So contrary to popular belief, you can see this animation that I borrowed, stole, whatever, from Wikipedia. We often think the planets circle around the sun in perfect circles. They're not. Right? The sun is not at the center of every orbit, it's just slightly off center. But if you consider the average path, the average of an ellipse is a circle. So by and large, we can work with that and keep our math nice and simple. So typically, his first law was pretty fundamental for Newton when he was trying to figure out his laws of gravitation. The second law says a line segment joining a planet and the sun sweeps out in equal areas during equal intervals of time. And that's basically saying, so that's what this one's sort of showing, aside from the fact that it flips. It's showing that, I don't know how well you can see, but there's tiny little white lines. And if you can just imagine every one of those little white lines is you can either think of it as a second or an hour, or if you want a day, it doesn't really matter. As long as you get the understanding that all these tiny little segments of this ellipse, if you want, circle, all these little segments all have equal areas, even though on this left-hand side, it's a bit smaller in comparison to this right-hand side, right? So this is more elongated on the right and a bit shorter on the left. But if you notice the triangles, the sections, if you will, all get slightly larger in vertical height, if you will, uh, compared to the longitudinal, the long end. So all of these share the exact same areas. So they all sweep out equal intervals of time, which basically means, if you can see from the arrows, so that their velocities are continuously changing. So the purple arrows, I believe, would be the acceleration in 2 dimensions, showing how the acceleration of the planet would be changing as it moves around the sun. And so therefore, the speed of any planet orbiting around the sun does not stay the same. It is constantly changing. It's going slowest when it's further from the sun. It's going fastest when it's closest to the sun. So as we go around Earth, as we go around the sun, Earth is constantly speeding up and slowing down. It's not a constant speed, contrary to popular belief. All right, his third law. There's the equation. You've probably been looking at it once or twice while you've been staring at the screen. Let's just go to the next screen, because the next screen is kind of a bit better, I think. I believe I forget which web page I stole this from. I did a Google search. Oh yeah, and this one has the second name known as the harmonic law. The first and second law, I believe the first one would be otherwise known as the law of ellipses. The second law would be known as the law of areas, if you want this other names for them. Sorry for the back and forth. So his third law is it's the Kepler constant. And that basically says for any satellite that's orbiting a mass. So you can think of this body as either the sun, or if you want, you can think of this body as Earth, and there's Earth's moon, and there's the, who knows what that is, random rock. And there's a satellite there. All masses that orbit the main massive body are considered satellites. Our moon is a satellite for our planet. Earth is a satellite of the sun, and the sun is a satellite of the big massive black holes at the center of the Milky Way galaxy. So a satellite's just a term for a mass that's orbiting around another mass. We too often just think satellite as, oh, telecommunication satellite. We picture these, which is fine. We just got rid of the name telecommunication, and we generally just call them satellites. And that's not a wrong descriptor, it's just not as specific. So if you hear the term satellite, it might be referring to one of these little guys. It might be referring to a moon or another planet. It depends on what the context is. So all Kepler's constant is saying, Kepler's third law is saying that for all masses orbiting around the same body, they're going to share the same ratio of their radius cubed divided by their period squared. They will all share that exact, not the exact planetary motion is a little bit nuanced, but they will all share basically the same ratio of their radius cubed to their period square. So that basically means all the planets that are orbiting around the sun are going to share pretty much the same value if you take their radius cubed divided by their period and squared. So the radius, I'm talking about the radius of orbit. So on your chart, it's a mean, it's the average distance to the sun. And of course, the period would be the time for it to go around the sun once. So 1 year, if you will. So every planet has its own unique value of the Kepler constant. Earth has its own. If you want to look and figure out what it is, all you just need to do is look at this information. Again, I'm assuming this is Earth. Look at the moon's information. How far is the moon away from the Earth? And how long does it take for the moon to orbit around Earth once? If you just if you cube its radius of orbit and you divide it by the square of its period, it'll give you a decent idea of what Earth's Kepler constant is, and that value would be used for every satellite that's orbiting around Earth. So if we're going to talk about orbits, then we kind of need to point something out. If you kind of consider what gravitational fields are doing, so gravitational fields are basically creating an attraction. So again, think of this as Earth. At all points away from Earth, as you move further away from Earth, you're still going to experience the gravitational field of Earth wanting you to fall back towards Earth. And it's going to be perpendicular at whatever surface that you're nearby. So it's always going to be pointing straight back at Earth. If you consider uniform accelerated motion of anything traveling around in a circle, the direction of its vectors for the acceleration will also be pointing towards the center. The only difference is we're talking about gravitational fields outside of Earth. We're not going to worry about what's going on inside the core, but outside of Earth, going straight towards, if you actually continue these on, if I drew them half decent, they would actually point towards the center as well. Right? But we tend to not think of it that way. So therefore, your gravitational field pretty much mimics that of your centripetal acceleration. The only real difference is Kepler told us the velocities aren't going to be constant. The speeds aren't going to be constant. They're going to be changing continuously, but we more or less assume that we're talking about perfect circles, and that is an average, if you will. So when something's orbiting a planet, the gravitational field supplies a centripetal acceleration. If you can get that down, then we now have equations that we can combine together to find out how to calculate orbital velocity and as well as orbital period. So from that, I'm going to start with speed because the equation is a little bit easier. If you remember, your equation for your centripetal acceleration for speed is your speed squared, your equation for centripetal acceleration that involves speed, your equation would be speed squared divided by the radius, right, as it's traveling around in a circle. If you use the equation for your gravitational field strength to be the value of the universal gravitation constant, and I left this as a capital M to remind you that when you're calculating the gravitational field, you want to use the large mass. So this would be the mass of Earth, right? This is not the mass of the satellite. It's not the mass of the moon. It's those masses cancel out completely if you even work back and do Newton's second law, which I did that on the previous video. So this is your basic startup for the equation of finding your orbital speed. As you can see, you have radius in both their denominators, so you can simplify that out and you can rearrange the equation to solve for speed so it's all by itself, and the speed of any orbiting body around a planet or a star or any large mass can be found by this simple equation. Gravitational constant multiplied by the mass of the large body, all divided by the radius of orbit. So the radius of orbit would be from the center of the large body to the center of the satellite. So all in the root, square root. So moving forward to period, pardon me. Moving over to period, using the same equation for your gravitational field strength and the equation for period when we are trying to find the centripetal acceleration with respect to radius and period, you combine those two equations together, and similar to the speed equation, when we do some manipulations, you can see radius is in two spots. So if we do some switching around, bring the period square to the top left, bring the gravitational constant and the mass to the bottom right, bring this radius squared to the top right, and then of course you'll have to take the square root, you'll end up with this equation where your period of orbit, so 1 year, if you will, if you're talking about the Earth going around the sun, or 1 lunar year as the moon goes around this Earth. To calculate that, you would just need to have to take 2 pi multiplied by the square root of the radius of orbit cubed divided by the gravitational constant and the large body, whatever we're orbiting around. So again, if we're talking about the moon, we would need to use Earth's mass. If we're going to talk about a period for Earth, we'd have to use the sun's mass. So whatever the large mass is that we're orbiting around, that's the mass that goes in there. Okay, so those are just 2 other equations to talk about orbital speed as well as the orbital period. And from that, I'm going to take the orbital period equation because this gets tied back into Kepler's third law. So if we look at this equation and we get rid of that radical and do some little manipulations, right? So first of all, if you square both sides, you get rid of the radical, you're back to period square. And then if you distribute that square throughout, you'll end up with 4 pi square, but I'd bring that down to the bottom and do, again, some quick manipulations. You would find out that you can actually calculate the Kepler's constant just by knowing the universal gravitation constant multiplied by the mass of the large body divided by 4 pi square, and that'll actually give you the Kepler constant for whatever the main body is that you're orbiting around. So if you want to find out Earth's Kepler constant, you would just have to take the mass of Earth multiplied by the gravitational constant divided by 4 pi square. If you want to find the Kepler constant of the sun, you can do one of 2 things. You can just look it up on the chart. I think it's like 3.35 times 10 to the 18 meters cubed per second square. Or you can just take any planetary information, the mass of any planet, the mass of the sun on any planet, take the mass of the sun multiply by the gravitational constant divided by 4 pi, and you get pretty much the same value. So, that was a mouthful. Sorry about the cough. I've got two equations, or two problems I'll quickly walk you through as fast as I can without it taking too much of your time. So suppose you have a lunar lander, so a satellite, if you will, that's going to orbit around the moon. It's to be placed in orbit around the moon at a mean altitude of 100 kilometers. So that means it's 100 kilometers off the surface of the moon. What will be the period of the lunar lander, and how fast must it move to maintain its orbit? So you're looking for period and orbital speed. So those are the two equations we have to work with. Information needed for this question. So this is pointing out all my givens. I need my radius of orbit. So I was given an altitude, and the altitude is not my radius of orbit. This is almost always the most common mistake when students are completing problems, whether it's on practice problems, whether it's your quiz problems, or whether it's your exam problems, or whether it's on your final exam. Too often, you'll see this number and go, oh, that's a distance, and you'll put it in place of the radius. An altitude is how far away it is off the surface of the planet, or in this case, surface of the moon. So we want to know what that distance is from the satellite or the lunar lander all the way to the center of the moon. So we actually have to add the moon's radius in order to get the radius of orbit. So the radius of orbit is not the same as the radius of a planet, right? So typically on your chart, the radius of orbit that's given on the chart is from the center of the sun to the center of whatever planet you're talking about. So we just need to know, and we don't really care about where the center of the mass of the satellite is, because we just assume that its center of mass is a number small enough that it doesn't really matter. It won't have any significant effect in this problem. So if we actually add the radius of the moon, 1.74 times 10 to the 6 meters, so it's pretty small in comparison to Earth. Added to the 100 kilometers, so 100 kilometers would just be 1 times 10 to the 5 meters. And just add them together, it'll change it to 1.84 times 10 to the 6. And then the other values, just one's a constant and the other one is the moon's mass. You can just pull those off the chart. That's where I got those from. Since we're going to do the period first, well, I choose to do the period first at least, get the harder one out of the way. And I only call it hard because, well, there's a lot of numbers to put in. So I'll just quickly zip through here. When you're plugging this through your calculator, really pay attention to how you're entering this all in. Too often, you're going to end up with issues with how you enter in your scientific notation, how you cube your radius versus how you throw in this denominator. So there might be some issues with bed mass while you plug this through your calculator the first time or two. So typically what I like to do is I'll usually figure out the numerator first. So if I cube that, I should end up with this. And often if I'm just trying to do some mental math to see whether or not I'm doing it right, I'll often ignore the number out front and just go, okay, 10 to the 6 cubed, I should have 10 to the 18, plus or minus 1, because it really depends on what numbers are out front, right? So if this was like a 3.1, for instance, and I cubed that, that would definitely turn this into 10 to the 19. So just, with a grain of salt, if I cube that, I should have at least 10 to the 18. And very often with my denominator, I'll just look at their scientific notation, 10 to the negative 11, 10 to the positive 22. I should be somewhere around 10 to the 11. But again, if you factor in the numbers up front, 6.7 basically times 7, roughly somewhere in the 40s. So that would add one more to the scientific notation. So again, just keep that in mind when you're doing your mathematics. And I always like to write out my numerator and my denominator as is, just so I can kind of visually check to make sure I wasn't making mistakes. So from there, you would just do a little bit of math, plug it into your calculator. But I also like to point out how the units work out, because these units are god awful, right? You have meters cubed on the top, you got Newton meter square down below, per kilogram down below. So I usually convert my Newton into a kilogram meter per second square, multiply by the meter square per kilogram square, and then sort of cancel out the things that cancel out, right? I'll go back one. So kilogram there, per kilogram there, those cancel out. I've got a meter there, I'm going to multiply by a meter square there, so those two together combine to form a meter cubed. So therefore, the meters cubed in pink also cancel out with the meter and the meter square there. And then because, again, that was kind of messy. Because I have this per second square in my denominator, whenever I have a denominator that's nested into a denominator, I can just bring it to the top and it becomes a numerator. And since the seconds don't cancel out, I should be left with a second square in my numerator that is trapped inside of a radical. And so if you take the square root of a second square, you end up with a second, which is perfect because we're trying to find the period. So mathematically, you should punch everything through and you should get roughly 7,000, almost 7,100, which is a little less than 2 hours. 2 hours exactly would be 7,200. So it takes about just a little under 2 hours for it to orbit around the moon once. Just leave it in seconds, if you will, because I believe that's what the answer is in the back of the in the note package would have it as. But if you want, if you see the numbers like this and you go, I don't know what that number even means, by all means convert it into hours or days or years just to get a better understanding of what those numbers mean. So that's your orbital period. So your speed, using the speed equation. I'm going to cheat a little bit because I notice I have a g times m there, gravitational constant times the mass and the denominator there. And I've already solved for that once. It was 4.8. I actually forget the number at this point, but I rounded up to 4.90 because I think it was 4.89 something. So usually when I do my math, I keep my numbers in my calculator. I don't round. What I write down is rounded. So I am going to use that number and put it in there and skip a step. So as you can see, I didn't write it out the same here. I just skipped that point, GM. There it is. And I don't have to cube my radius in the denominator. It's just the radius as is. So 1.84 times 10 to the 6 meters. So you can work that through. You can cancel off a meter there with the square there. And then if I carry this Newton meter per kilogram forward, so my Newton again is a kilogram meter per second square. So my meter combined with a meter becomes a meter square per second square. And this kilogram will cancel that per kilogram off, which is great. And so that is, and of course it's all in the radical, so my units will work out in the end. So those are just things you can check to make sure you've set your equations up correct. So you get roughly 1,630 meters per second, or 1.6 kilometers per second. So that's pretty fast. So after all, it's going to go around the moon and only take about 2 hours. So it has to be going pretty fast. So the last question I'm going to go through with you, you're going to need to understand this term called the astronomical unit. So the astronomical unit is just a placeholder unit for astrophysicists and cosmologists to really get an idea. It's a benchmark value, if you will. So if we're dealing with planets and asteroids and things that are inside comets to things that are inside of our solar system and maybe even just slightly away outside of our solar system in interstellar space, we often refer to distances in terms of astronomical units, mostly because it simplifies a lot of the math, and it's still too near to even bother with using a light year. So we tend to use light years when we're talking about things that are ridiculously far away, well past our solar system. So when it's within range of our solar system, we tend to use an astronomical unit in place of the meter. So the astronomical unit, again, is the distance between the center of the sun, drawn not to scale, to the center of Earth. And that's typically good enough for the moment. So I'm going to relate that into a question involving the Kepler constant. So Kepler constant is often used, actually it's not used too often value-wise, but it's used as a nice ratio. Here's what I mean. Suppose you have a planet discovered whose orbital period was twice that of Earth. How many times further from the sun would this planet be? So this is kind of a made-up question here, but they use this a lot to determine some of the information about Jupiter's many moons, which at this point, last I checked, there was 72, but I heard recently they found a bunch more. So I don't know how many moons there are for Jupiter right now. And by the time you watch this video, who knows, maybe they'll find another one. So I'm not going to use Jupiter's information. So with this question here, things to point out, I'm going to use the astronomical unit as one of my radiuses. And I'm going to use a simple value for my period as 1 year. Just again, I could call it convert into seconds if I want, but I'm going to keep my number simple until I don't have to. So I'll read the question one more time. If a planet were discovered whose orbital period was twice that of Earth. So we're talking about an orbital period of Earth. That by definition is 1 year. So this other planet takes 2 years according to what that question asked. How many times farther from the sun would this planet be? I'm looking for this other planet's radius of orbit. So if I understand the Kepler constant very well and Kepler's third law, then all planets orbiting our sun should share the same Kepler constant. So therefore, I can either use these values here in meters cubed per second square, which is kind of what I wanted to point out, but I'm not going to. But that is one method I can use. But if I am going to use these values here, remember, meters cubed per second square, do not compute with my astronomical unit and my 1 year. So these are different units than this constant value. So I'm not going to use this, but you can. You just have to convert this into 1.49 times 10 to the 11 meters. You have to convert that into the 8.61 times 10 to the 4. This one, 3.16 times 10 to the 7 seconds. So yeah, even I make that mistake. All right, so moving forward, I'm not going to use that value. So instead, I'm going to recognize that my unknown planet is going to have twice the period of Earth. So technically, I either say 2 years, or I can leave it as just 2 times the period of Earth. If I actually plug that into the equation, I now have an equation that looks like this. And then I'm going to proceed. I'm going to bring that 2 times the period of Earth squared above and to the left, right? As you can see right here. And then if I square it, I end up with 4 times the period of Earth squared. So I distribute the square into both the numerical term and the variable. And I have the period of Earth squared in my numerator. I have the period of Earth squared in my denominator. Those cancel out, and I'm left with 4 times the cube of Earth's radius of orbit should be equal to this unknown planet's radius of orbit cubed. So you need to get that all by itself. So take the cube root on both sides, which is nice as far as the cube root's concerned, because it's going to get rid of both those cubes. 4 to the cube root is just slightly less than 1.6. I just didn't bother typing in any more decimal places. And so you have a nice ratio. You got 1.6 times Earth's radius should give you the radius of this new planet. So you can either call that 1.6 astronomical units, because again, by definition, Earth's radius is considered 1 astronomical unit, right? So how many times farther from the sun would this planet be? 1.6 times, or you can just call it 1.6 astronomical units, which is what it's getting at. If that's not good enough for you and you want a numerical value, this is what the question is looking for. But if you remember again, an astronomical unit is technically 1.49 times 10 to the 11. You can get a value in meters just by multiplying 1.6 times roughly 1.5. And this puts it just slightly further than Mars, which if I were to guess, might be Ceres. I'm not going to look that one up, but that's slightly further than Mars. So otherwise, it's just some unknown made-up question. And hopefully you see how this math gets pushed through. So you're going to have a couple of questions like this in your work problems. You might be solving for the radius, you might be solving for the period. So just kind of get the idea of how to work this equation through. All right, that's probably longer than I want it to be, so I'll stop here. Again, if you have any questions, just send me an email and I'll try to work you through it. So good luck with that, and see you again soon.